will not take too much of your time. Okay, it's my honor to introduce Professor Susan Athey. Susan is economics of technology professor in Stanford and has too many engagements. I can talk about all of them, so I will talk about some of those I know. When I was at Microsoft many years ago, we will not reveal how long that is ago, but she started off doing empirical economics already at that time, starting to bring together econometrics and machine learning, first in a little research group at our lab in Cambridge. Then she became the chief economy officer, and she actually helped move Microsoft from the stone age of shrink-wrapped software to the modern age of search engines, where you have platforms and you have sort of agents on several sites, and the people who pay you is not the people you pay, and she was very influential in that. And since then, she has served on many, many committees, including various committees for various countries, from Canada to lately the US, where from 2022 to 24, she was Chief Economist of the U.S. Department of Justice Antitrust Division. And with that, I'm looking forward to your talk, Susan. It's wonderful to have you.
Great. Thank you so much. It's great to be here. Thank you so much for having me here. So giving interdisciplinary talks is always really hard. And of course, you don't always know who's going to show up. We did this great conference at Cornell recently with a econ CS mix, and one of the funny things we were joking afterwards is how the econ talks were all full of equations and the CS talks were all full of pictures. And then here we have a bunch of people at the intersection, so it's hard to know everyone's preferences and optimize for them. On top of that, some of the stuff I'm going to talk about today I think is going to be pretty unfamiliar to the CS side, but I think maybe quite useful on the CS side, but I'm going to do it in the context of a labor market application. So there's going to be sort of two intellectual steps if you want to think about how it matters for you. One is like to just understand what I'm saying, which will be kind of unfamiliar. And then there's a second step to think about how you might port it over. And I'm not going to show you that today because I'm not going to have time. And I haven't fully done it. But I'm going to try to put little signposts all the way through about how you would translate this over to the world of large language models. Okay, so apologies in advance because I'm going to try to do everything everywhere all at once and surely fail, but hopefully plant a few seeds along the way. So this is a research agenda that I got started on, luckily for me, well before ChatGPT came out. And I've had a long-standing collaboration for about a dozen years with David Bly, who I'm sure many of you know, and a product of a cousin of or a sibling of many people in the room. And through David, started working with Kian Vafa, who has been a postdoc at Harvard and is on the job market this year, doing quite well. And so this collaboration was basically trying to, along the whole collaboration I've had with David, trying to merge ideas from natural language modeling techniques and generative modeling and causal inference applied to economic problems. So we started working with Kian on the problem of studying labor market transitions. And we have a whole series of papers that I'm going to run through today. And the thing that was really great for me personally is that I'd already felt in a leisurely way had a chance to kind of get my hands dirty and think about the models before the whole world got interested in them, which maybe gives me a slight, a tiny moment ahead in terms of thinking about what you do with them. The co-author team is interdisciplinary. Ayush was a computer science student. Tianyu is an engineering student. Emil came from economics and is now in marketing and CS at Northeastern. Ellie was an econ PhD. So, and this is kind of a microcosm of my lab. Okay, so I'm going to go really fast through the introduction because everybody kind of has the big picture, so I just want to anchor how I'm going to connect. So, foundation models for machine learning. Machine learning models trained on lots of data that can be adapted to downstream tasks. So you could actually reinterpret some of my previous work with David Bly as foundation models for shopping. But we built them with Bayesian models before the latest thing came out. So they're self-supervised. They make use of embedding functions, transforming high-dimensional data to low-dimensional vectors. And then this idea is what I'm applying in a lot of this work, fine-tuning. So training the model to fit well on smaller specialized data sets. And especially from the perspective of working in subdomains that have proprietary or specialized data, like data on health outcomes or data on individual worker wages. ChatGPT doesn't know it all. Some of it knows, but some of it can't know, and it's not magic. And so it's going to get the information that we give it, and so we want. And then in addition to that, in many economic applications, we really care about getting conditional distributions correct. Like we care about accuracy in terms of conditional probabilities that are matching a particular target data set. Okay. The second thing that's going to be really useful and exciting to me as a social scientist and as an econometrician about fine-tuning is that fine-tuning is something that's done like with stochastic gradient descent, which means I just have to put in a gradient. And in econometrics, we don't usually use predictive gradients. We use other gradients of other moments that are related to what we want to estimate, like a causal effect or an elasticity or something else. And sometimes we use multiple moments to characterize something. We have other restrictions, like monotonicity restrictions. And the beauty of fine-tuning is you can let somebody else spend all their money and do the work to create a basic data set, but then I can just change the equations and march the thing along and make it do what I want to do for a downstream task. And I think that that's gotten a little bit lost in the thinking about general artificial intelligence and everything else. It's like, but from a using this whole architecture for science perspective, the fact that I can control the objective and change the objective to be what I want it to be, I think is incredibly powerful as a research tool. And it's also really powerful as a tool for an academic because I don't have $100 million to go retrain something, but I want to engage in this research endeavor. Well, fine-tuning is a stage at which I can engage and make progress. I'll also mention that even in the world of LLMs, I just got back from Africa. I'm working with the World Bank on the World Development Report 2026 on AI. I met with all these entrepreneurs and people developing models all through Africa with all these dialects, and they're fine-tuning open models is a big thing. And it outperforms the general models because the general models don't have the data and the labs don't care how well you do in the dialect of Swahili, so they don't work well. But also a lot of proprietary data is local, and so again, you would want to use that, but you don't want to reinvent the wheel, you don't have the money. So this is a very exciting, I think a very exciting area for low resource environments, academics, and just for using these models as a tool for science. And so that's what I'm really using today, is I'm going to use this whole tool and infrastructure for science. But along the way, in my little microcosm of a lab where I'm doing things for science, I think there are insights that you could port back if you worked at OpenAI or Anthropic. Okay, and I should say, when I do present to those labs, a lot of people are interested in these ideas. And so it's a two-way conversation between them of the problems they're facing and me, the research I'm doing. So empirical questions. So I'm going to be building predictive models of worker transitions. And from economists, we don't have many in the room, economists who are still back in the dark ages that everything should be a regression, ask me, why would you even care about a predictive model? So believe it or not, in 2025, you can go and give a seminar at MIT or Chicago in economics and have people want to argue with you for 10 minutes about why you should care about predictive accuracy, despite the fact that there are theorems that tell you why you should, even if all you care about is a causal effect. That is, what the theory of statistics tells you is that having better predictive models supports causal estimation. The problem is, though, that a lot of times we're interested in estimating these problems on small data sets, and we want to maybe use some techniques from machine learning and AI, but we're not really sure how they're going to work given data size, availability, representativeness. If we use biased training data? Is that going to lead to biased output? Those are the kinds of some of the questions that we think about. And my answers, and I'm even across papers I'm not showing you today, is like, no, actually. Like, I mean, yes, of course, you have to, your final model is what's in the data, but if you fine tune to the appropriate data set, you can give it the properties you want, even if upstream you built on something that was non-representative. And I quantify, again, in some papers I won't show you today, that trade-off and show that adding more non-representative data is helpful, in fact, although it could be worse. Then today what I said, I'm going to tell you some things that were going to be less familiar. There's a tool, and it's really it's a descriptive tool that is very popular in parts of economics, also very popular in sociology and other social science disciplines, which even those of you who've been working at the intersection of machine learning and causal inference probably haven't heard that much about, because it's not causal, and it's called decomposition. And so, and I'm going to show you mathematically and statistically, they're actually the same, very closely connected, methodologically the same, but the interpretation is different. And so decompositions are basically asking us to understand variation in output. They're asking to understand the sources of differences between two groups. Okay, so we can imagine, just to build this up a little bit, what if we were querying a large language model and we experimentally varied one attribute of a prompt? So we gave it a prompt, but you said, I'm a woman who has a headache, or say I'm a man who has a headache, and you want to compare the differences in the output. So that's a comparison between two groups. Gender is the variable you're comparing by, but then you have this complicated output that you would want to summarize. Now, even in this simple world of experimental variation, so just two different prompts getting different responses, the outcome is the response, we can think about decomposing the differences in the responses and saying, like, maybe they start out the same, like maybe the first paragraph is the same for men and women, but then they evolve to be different as they go along. Or maybe like the plan is the same in a thinking model, but then the implementation is different. So if we think about both the sequence of thinking and planning as well as the sequence of text that comes out, we might want to understand how much of the final variation, like should you take a Tylenol or not, at the end, is coming from different parts of this sequential process. It is very hard, actually, to systematize that or operationalize that. If you're a lab and trying to say, well, why are we getting different answers? You can ask that high-level question, why are we getting different answers, to a data scientist, but how would they systematically break that problem down and come up with numbers across lots of different domains? So decompositions is like a tool for doing that. It's a way to systematically think about sources of variation. We could, and so then if we said, what's a good answer? We were talking about that earlier. It's also like, a big part of the value added in all these AI models is actually just deciding what a good answer is. And so in some cases, we can think about having a target data set and wanting, say men and women do get different answers. Maybe that's fine, because in the target data set of health practitioners, they also get different answers, because maybe the reasons women get headaches are different than the reasons men get headaches, and so there should be differences in those. So maybe on average there should be differences, but then maybe conditional on a bunch of variables, they should be the same. And so we want to understand how much of the male-female differences is it should be there, maybe hormones as a cause or something, but how much of it shouldn't be there, that once you condition on a whole bunch of variables, you should actually be getting the same answer. So a decomposition would help you separate those two sources of differences. Okay? It's not causal, it's not about causal estimation, but it's very useful as an accounting exercise. Like if you think about, if I told you men and women are giving different answers, but I told you that conditional on 15 things, they get the same answers, you're gonna address maybe you don't even think you have a problem, or if you do have a problem, you're gonna think about it very differently than if they have very big differences conditional on their characteristics. Okay? So this is saying just using a little mathematics, using a little bit of simple mathematics, like conditional probability, concepts from conditional probability can help you operationalize these kinds of comparisons and be systematic about them. Being systematic then has this benefit of interpretability also, that like, I can talk about bias, but what the heck does that mean? But if I talk about conditional probabilities and whether they are the same or different as a target data set, well, that has a meaning. It's not the only thing you're interested in, but at least it's concrete and it's well defined. We're talking about the same thing. All right. So finally, one thing I'm just going to preview, and hopefully if I talk fast enough, I will actually deliver on this. We'll see. Is that the stuff I'm going to present at the end of the talk also connects directly to a literature on off-policy evaluation and reinforcement learning. So we're actually developing techniques that are applicable for that problem as well. OK. Operationalizing the agenda, some of like the tactical questions. Can foundation models improve causal analysis? And I've got a bunch of papers saying yes. What is the role of fine-tuning and how should it be done? When is it good? What's the interaction between model size and data? Fine-tuning to fit multiple outcomes. How can I change the objectives of fine-tuning methods to try to get them to answer, to really focus on the questions I want to do or accomplish the downstream tasks I'm interested in? And what new questions and opportunities arise once I have these very powerful models that are tailored to my downstream tasks. What is the new world of questions that opens up? And that's, again, it's not so easy, actually. Like, OK, now I do have a rich model. What if I can predict for every person in the economy what their next job is with high accuracy? And I can look at the causal effect of training programs on them. But what do I do with that? How do I show it to you? Because that's like a big, complicated, non-parametric thing. Like, I could show you a 1,000 by 1,000 transition matrix, but like, what are you going to do with that? So I still have to like figure out how to interpret it and present it in a way that's useful. And so that's an ongoing journey, I would say, and I'm just going to show you some stabs I have at that. OK, so starting with this problem of wages, we're going to start with wages. There's probably like 100,000 papers in economics that try to predict wages, and they have many reasons for doing that. It's partly as an input to causal analysis about education, training, urbanization, everything else. Sometimes it's got other purposes, but let's just take for a moment that this is massive literature, and probably like 1 million regressions have been run by research assistants of this form. And so what are they trying to do? They're trying to take worker history and predict wages. Again, maybe with the downstream task in mind, but this is the empirical exercise. But it's actually just too hard of a problem because if you think about all of the possible sequence of jobs in the past, that space is too big. And so if you literally had indicators for every possible instance of a job history, that's more job histories than there are people on Earth, so I obviously can't estimate the model. And so that is the dimension reduction problem. So how do we, and so in economics, say how did we do that, is that we would create summary statistics from the history, and over the 1 million regressions that our research assistants have run, we have come to conventions about what we should put in there. And it's usually like last job category, like 20 dummies for the last job category, how many years of education, maybe how many years you've been in the current job, and a few other things. Okay? And we all run the same regression. Okay, so I'm going to show you some results from that regression, but it's just like not a regression I pulled out of the air. This regression is something that we converged on after lots of iteration.
Is the intention of these models to be predictive or to be causal?
So I'm right now lumping that together. So a very common thing is to have this predictive regression and then put a dummy variable in it for did you have a training program? Or did you go to college? Or are you urban? That regression is one implementation of a causal analysis. And the statistical theory of that causal analysis says that the quality of your coefficient on training program is dependent on the quality of your predictive model. Because if your predictive model is poor, it may omit variables. I'm going to write this down later. You may have omitted variable bias. And the precision of that model also drives the precision of your causal estimate. So, but that's the motivation, although frankly, until relatively recently, most economists did not spell out everything I just said. They just ran a regression, put in a table, and talked about the coefficient. And so that's why the economists are confused when they say, why do you want a good predictive model? Because they didn't think about it that way, because they just ran the regression. But if I analyze the regression they were ran from the theory of semi-parametric statistics, I can prove that, in fact, a good predictive model answers their question better. Okay. Sorry, I just compressed semi-parametric statistics into 30 seconds. Hopefully that was intelligible to someone. Okay, so how would we do this from foundation models? Well, we have these, in the US, we have decided not to invest money in collecting administrative data that is representative. So we have data sets with 10,000 people that we follow over time. In Scandinavia, they have all their people, but they don't have that many people. So that's a problem. There don't exist countries the size of the US that have administrative data for all their people available. So in the US, we have these very small data sets of watching people over time. But places like LinkedIn, people post their resumes. And so we actually we bought this data set of 23 million resumes from a variety of sources. But those resumes, even if they have wages, usually actually, the people will sell you wages, but those are just imputed from the census data, from the same data that I have. So they're imputed. They don't have more data than I do. Sometimes people self-report wages, but those are self-reported. So we have big data sets that basically don't have wages. They're also non-representative because a lot of people don't put their resumes on LinkedIn. We're going to use that as if this is our analog of Reddit, right? So the scraped resumes are all the data the language models used, and these are the scraped resumes. And we're going to think of a sequence of jobs just like a sequence of words. Okay? So we're going to build, and so we built this on Stanford machines because we only have 23 million resumes, and there's only 330 jobs. So this is a large language model with a small vocabulary. Okay? So, and by the way, just as progressive science, this is a good progressive science, I think. Make your own little laboratory, and then you can play in it without $100 million. Although if somebody wants to give that to me, I'll take it. But actually, I wouldn't spend it on this if I had it. So, transition distribution. So the transition distribution would be then what a transformer model is. It's just a next word prediction. It's autoregressive. I'm going to take, but essentially what I'm going to do is try to fit these conditional probabilities. Getting quality representations is the biggest challenge, and the resume data is going to help. Of course, the loss function for training the transformer is going to say that two embedding, so lambda sub theta is the embedding function mapping from histories to a vector, a latent vector. And what the loss function is going to say is that two job histories are similar if and only if they have the same conditional probability predictions. And so this will be useful for my wage prediction model if the two job histories that have the same probability distribution over subsequent jobs also have similar wages. So it's kind of just putting a distance metric, and if the distance metric for next job distributions is similar to the distance metric for next wage, it will be useful. Will it be perfect? No. Might it leave things out? Yes. But it's probably better than sticking in 20 dummy variables and a summary statistic that you as a human crafted. So then what we're going to do in this pipeline is we'll build our foundation model on the passively collected resumes. Then we will fine-tune them on the longitudinal surveys. And our first paper in this series was looking at this as kind of like a fine-tuning as a transfer learning problem, and looking at this first question of, well, maybe I should, why don't I just train a transformer model directly on this data? Adding this data could make things better or worse because this data is non-representative. So in principle, all the data I should need for predicting wages in my survey data set is in my survey data set. So, but yet, using this passively collected data helps you. And how does it help you? Because it helps you learn the representations. It helps you learn the meaning of jobs, which you then apply. It's like you can think of it as like a variable selection approach that helps me with my downstream task. Of course, I didn't know whether it would help, but it helped a lot. So that was the insight. This is not shocking at all to you machine learning people. Of course, it's more shocking to economists who are offended that their regression model didn't win. Okay. So, fine tuning, I think probably everybody here knows, but I'm one of the things that you might not think about all the time is that not only does fine tuning allow you to continue the training of an original foundation model with a smaller data, it also allows you to change the objective function. So the next job prediction was what I did in my pre-training step. In the fine-tuning step, I changed my thing to be now a wage loss function, standard mean squared error loss function. But of course, when I take the gradient of this, there's two components. One is the y minus mu hat, and the other component is the gradient of the embedding function, which is the same gradient I was doing before. So it's like trivial to just change your objective function and keep marching along. Okay, so then the first thing we do, because it is a bit of a horse race, we start with the standard regression model as of the latest survey papers for wages using coarse-grained occupations. We then also run the regression with fine-grained occupations, so just categorical variables, dummy variables for the 30 categories, and we also use lasso in that regression framework. Then the horse race is against those versus taking our embedding function and then embedding it in a shallow neural network and using it to predict wages that way. So this is still like the embedding function is entering the wage through this shallow neural network. And so actually economists, because they're running simple regressions, don't even use held out data, but we, of course, are using held out data. So these are the held out R-squareds from the standard economics model. So they explained about 42% of the variation. And the model that we have explains 52% of the variation, which is a big deal. And it's especially a big deal, as I'm going to show you, because the stuff that we were missing is also correlated with other things. So in particular, if you were using this for a causal analysis, the stuff that we were missing is really important stuff. And it's important stuff that's correlated with treatments that you might be interested in. So I'll show you that in a minute. Okay.
Susan?
Yep.
What happens if you do career but without including the economist's traditional controls?
That is a good question. So we actually I didn't really show you this, but well, here we have them in linearly. We also, in some versions, put them in as part of the neural network. They're doing some work, but it's sort of like you could do it. It's a good question, actually. So I think we have done that at some point, and I think they do matter, but like not a huge amount. And part of it is it matters the order in which you think about it, because like you can kind of infer education from your whole career history. So you have to actually ask the question carefully. So if the question is like, does education matter? Yes, hugely. But like, does sticking in education as a variable on top of these histories matter is a different question. In some version, we had all of these accounting exercises, but actually I haven't looked at them lately. Okay, so then we go to the part now that's going to be less familiar to folks, even in the causal literature. So there's a bunch of equations. So here I'm going to be a good economist. But these are familiar, these still should be familiar equations. So the first line is, so I'm going to talk about now gender wage decompositions. And here the question, and again, just the gender wage gap is the subject of tens of thousands of papers. So like very, very popular, or gender, race, there's like a couple of them that are hugely popular in both economics and sociology. People do it across country, all sorts of different variations of it. The thing at the top is just the difference in wages between men and women. Okay, that's called the raw wage gap. Now, and so you see politicians, like Hillary Clinton said a lot of this when she ran for president, like, women make 80% of men, or women make 75% of men. Now, clearly, like there's a little bit of accounting missing there. And so this exercise kind of shows you the accounting that would give you a more interpretable number. So the first equation here is just using iterated, and so, by the way, everything on this page is just iterated expectations and Bayes' rule. There's like nothing deep here. The first equation is just using iterated expectations. So we've got on the outside, the history is conditional on gender, and on the inside we have wages conditional on history and gender. Then the decomposition trick is to add and subtract this term here, which is, here we have female, female, here we have male, male, male histories, male wage function. And the thing we're adding and subtracting is a mismatch, female histories, male wage, okay? now we have two terms which you could argue are more interpretable. The first one is I'm going to hold histories fixed and say and this is basically asking, on average, if everybody had the same job histories as women, what would be the wage gap? Okay? The second equation, the second line of the equation says, what if we had the same wage function? What if men and women got paid the same conditional on history? What is the difference from different histories? Okay? And the argument is this is just accounting, literally just accounting, but the argument is this accounting exercise is a useful accounting exercise, because if I told you that conditional on history, that men and women got paid the same thing, the politician on the stump might have a slightly different take on it. Whereas if I said, and they also might say, gosh, you know, whatever, this raw wage gap is accounted for in some sense by history differences, and so maybe we should think about educational interventions and career counseling and things like that. Whereas if if everything is about different wages conditional on history, then maybe we should be thinking about bargaining and child care and other things that make that difference. So even though this isn't causal, it's like shining a light on where you should go look to do an experiment or evaluate a policy.
Sorry,
Yep.
understand, what is it making, so from the second line to the third, when you're making F red, and what does it mean, what does the color scheme mean? I'm missing that.
Sure. So I'm just trying to show here this outer thing. I'm holding. I made green here the thing that's the same, and red the thing that's different. So out here I've got the same histories, and I'm changing the wage function. And here I've got the same wage function, and I'm changing the histories.
So this would be the expected wages if it was a man with the same history. So the history is different if it's a man and a woman, right? So
Yeah, the history distribution is different.
right.
Yeah, so this first line is just saying there's two sources of difference. One is the distribution of history, and the second is the conditional wage conditional on history. And this is just a very powerful decomposition. Now, this decomposition itself is the genesis and the foundation of Pearl and Rubin and all of those causal models, because they take this equation here, they basically do that same decomposition, then they take this equation here, and they say this equation, which is holding histories fixed, changing the wage function, under an additional assumption has a causal interpretation. So under unconfoundedness, which is that conditional on history, the gender is randomly assigned. If conditional on history, so that now imagine it's not gender, it's a training program, so just go with me. If it was conditional, if G was randomly assigned conditional on H, then that equation is the same as the causal effect of G, which can be written either in due calculus or in potential outcomes notation. Yep.
This could be the wage of a man who gave birth, for example, now, right? So we are leaving.
So we do not do this step when this is actually gender. Like this doesn't really make sense for gender, or at least you have to be really careful what you mean. Like, do I take a resume and then randomize their name? So people don't do this step when it's gender.
Okay.
But so the reason I'm putting this up now is if it wasn't gender, if this was a training program we were talking about, this equation is one of the most widely studied equations in statistics, and there's well-established statistical theory for that equation, and it's, you know, this is Pearl, this is Rubin, this is everything. Decompositions, therefore, target the same estimand, because all of the philosophy and the assumptions and everything is about the interpretation of that thing. So you make more assumptions to interpret it as causal, but the statistics, the estimation theory, is about estimating that thing, and it's the same thing. So the statistics of decompositions, the statistics of the estimation of decompositions is equivalent to the statistics of the estimation of causal effects under unconfoundedness. So this is very confusing, but it's a fact. So I'm going to do decompositions today. It would be easier to talk about it if I was doing causal effects, and I thought about writing this whole literature on that, but then I said, well, but then people are going to argue about whether unconfoundedness holds in my application, and rather I'll just do decompositions, because then I don't have to argue about it, and the methods are the exact same. So I'm doing decompositions, and I'm not going to argue about unconfoundedness or whether it's meaningful to change a gender or anything else. I'm just doing accounting. Okay. But the other reason I think this is a useful way to go is these decompositions actually have wide applicability, and that's, I think, in understanding your language models and understanding any model. I think the decomposition tool is much bigger than the causal tool. Okay. All right. That I already said all of that. Okay. So now let me briefly tell you my statistical theory, and then I will start. I will even make it more complicated in a second. But this is my main statistical theorem. I'm going to show you one statistical theorem today, and this is it. I'm building towards it now. So how do you estimate this thing? So as I said, estimating this thing is one of the most studied questions in statistics, in modern statistics anyways. The answer is there's like 3 ways to do it. One is outcome modeling. So we literally just estimate this regression function. We take the inner expectation and we use supervised learning to estimate it. And then once we've got the inner expectation, then we can we can reweight by the female histories, and we'll be done. The second is I can do propensity weighting. So I can just take the actual female wage data I have and the actual male wage data I have, and reweight it so that the distributions of histories match. It's like kind of like transfer learning, and then look at the difference. Okay. And the third, what's semi-parametrically efficient, is to do a doubly robust combination of both. And so in this augmented inverse propensity weighting, or double machine learning, it was rebranded as double machine learning, which was, I give all the kudos to the rebranders. It's worked very well, double machine learning, but the original statistical term was augmented inverse propensity weighting. Is root inconsistent and asymptotically normal if this thing converges at the right rate. Okay, before your eyes glaze over, this is actually like a useful theory, because it says, gosh, in the machine learning land, it's really hard to get a regression function right, and it's really hard to get reweighting right. And if you assume that you got them, either of them, if you want to assume that you got them right, you're probably fooling yourself. But if I use these double robust methods, I basically combine things. So I first use the outcome model to like adjust everything. So I kind of take the residuals. So I see what I can explain with my regression model, and then I reweight. And that kind of gets rid of errors in both. And then what the modern literature also does is something called cross-fitting. So we use different data to get different terms, and that kind of avoids like multiplicative errors, and we get very well-performing methods. Okay, so that's where this literature leads off. But I should say, like the double machine learning paper has, I don't know, 4,000 citations or something in the last few years. So this has been very, very popular recently. But it has a problem in my application still, because it's assuming that you can get the regression function right, and you can get the propensity model right, or the reweighting model right. And that's kind of crazy if I think that my covariate space is like indicator functions for all possible histories. Okay. You say, but okay, well, why don't you use dimension reduction? But we didn't have good theory for the workflow that everybody would do, I think, in the future, which is that actually in the workflow of the future, you're going to use some kind of foundation model for the dimension reduction, and then you might do it on a different data set, on a different computer, whatever, and then you might like port it over to your applied problem, and we want the theory to match that. So what we did here is we said, we're going to take that same condition, like that we have a good enough regression model and we have a good enough reweighting function, and we're going to write down the conditions as a function of our low-dimensional embedding rather than the full history. And so this condition says, oh, if I run my regression on my 80-dimensional embedding vector instead of the full history, this condition is saying I did that well. But of course, that can't be enough, because I might have a really simple embedding vector that throws all the information away. So that can't possibly be enough. So we have to put some condition on the quality of the embedding if we're going to focus on how well we do conditional on an embedding. And so we introduce this condition, which is that the omitted variable bias goes away. And so what this is basically about is I'm going to change my objective function to focus on the thing that actually matters. Okay? So I'm going to build up this omitted variable bias estimation in a couple of steps. The first is the big picture of like, wait, why isn't prediction good enough? Why isn't supervised learning the answer to every problem? After all, it can ace a math test, so, you know, I mean, the semi-supervised learning, like why do I need a different objective function at all? So if I was doing just a predictive approach, what I would do is I would fit a supervised learning model to try to make my embedding function do a good job matching the true conditional expectation. So what I would try to do is match A1 and B1. That is, I'm going to try to fit the true conditional expectation of wages using my embedding, and I'm going to try to match them up. And the same for min, and that's how I would get my, that's the standard objective for supervised learning. But from the perspective of doing decompositions, what I care about is the difference. So I don't actually need to predict wages well. I need to predict the difference between men and women's wages well. And so this same insight was the insight behind some of my most popular work on heterogeneous treatment effects, and I'm just porting this insight over here. It can make a huge difference, because if you give a model with limited data a job and you tell it your job is to predict wages, it's actually pretty easy to predict wages. There might be some, it's actually very hard to predict gender gaps. So your model might just regularize away the things that matter the most for differences if you tell it to do prediction. And so that was a big topic of my early 2010s work, was showing that was true and then providing software and objective functions to optimize something different. Now you say, well, but how can I optimize for differences? Because I don't see the same person being male and female at the same time. That's the fundamental problem of causal inference. So you can't immediately solve the problem. But in fact, there are good ways to solve the problem, which I'll show you in just a second. First, let me just show you what the omitted variable bias term looks like. So this term is equal to the bias you would get from plugging in an embedding and instead of plugging in the true history, if your goal was to get this quote unquote causal effect of gender. Okay? And so the bias is it's a covariance. So the mistake that you would make from leaving something out of lambda of h, of having a regularizing away part of h, you make a mistake if you leave out something from h that predicts gender and also predicts wage. That's what we call an omitted variable. That's a term of art in economics, and those omitted variables are crucial. We spend in an economics seminar, you spend half the seminar talking about omitted variables. So we really want to get rid of them, and so what we're saying is, if you do get rid of them, that's the sense in which your embedding has to be good enough. I want to make sure that I train an embedding that picks up anything that's both correlated with gender and wage. And this is a different objective than the predictive objective. Now you say, but how would I operationalize that objective? How would I turn that into something I stick into stochastic gradient descent? Well, we've already done that. And my generalized random forest software package, which is also very popular, already has used exactly this objective. So my generalized random forest package said, let's take random forest and change the objective to be a causal objective. How did we do that? Well, we turn a causal problem into a predictive problem by using what's called a residual on residual regression. So we try to train the model to minimize the gap between the residual of a regression of wages on history and a regression of gender on predicted gender. So that residual on residual regression gives you a causal effect. This is called Robinson's regression from the 1980s, and it's been popularized in semi-parametric statistics. In the modern machine learning era, my co-author, Stefan, relabeled it the R-learner objective, like a regression, residual on residual regression objective. This objective performs extremely well. It's got great statistical properties. So I'm going to take that objective out of the world that they've used it in, plop it into my stochastic gradient descent, and optimize for it. So making a transformer model causal, it's still not completely easy because I haven't told you how I've got to estimate these regressions too, and it's actually an iterative process, so there's a bunch of other stuff I won't have time to tell you about. But it's only a few steps away from a two-step process where you run a couple of regressions and then plug a residual on residual regression into a stochastic gradient descent algorithm. So it's it's so easy to do. I have the idea, I get the results the next day. Beautiful. Okay, so what we find is when we actually use the R-learner objective, our predictive accuracy gets better. So that could be wrong, that could be the opposite result. Like, you should think that if you use a predictive objective that you do better in a predictive evaluation, but actually using a causal objective does better in a predictive evaluation than using a predictive objective for predictive evaluation. And my interpretation is it's regularizing in a useful way, actually. It's kind of guiding, it's somehow guiding the model towards getting more structural, causal, foundational world models. But it could have gone the other way, for sure. All right. I promised you some interpretability, so let me get started on the interpretability here. Yeah.
It could have gone the other way around. Is that just an empirical fact?
Just
a theorem, and it could have gone the other way around?
Yeah. So I think in general, you would expect, absent regularization issues, like with enough data, it should be that you do best for an objective when you optimize for that objective. But in an imperfect world with limited data, anything can happen.
And your empirical data show that that's what
yeah, exactly. That the counterintuitive things happens rather than the intuitive thing happens. But this is very related. It's not that uncommon, actually, like multitask learning and machine learning. This happens a fair bit, that like optimizing for the wrong objective helps you with another objective. It's all about signal to noise ratio and things like that.
But there's no theory about
No.
it which says it's a better regularization if you have less data?
No. I mean, I think that qualitatively, most people who have thought about the multitask issue can outline the trade-offs, but I think it's so qualitatively kind of understand what would lead it to go one way or the other, but I think it's just gonna depend. It's like a small sample property, basically. Okay, so I promised you a little interpretability. So in economics, over decades, for any particular style of empirical work, we come up with like 6 graphs. We all agree when you do this, it's a certain analysis, you have to show me these 6 graphs. It takes decades to like figure out what the graphs are and what they mean, and arguing in seminars and stuff. So I think that like the descriptive analysis of these high dimensional transition models and stuff is, and embedding models is still it's in its infancy. So here are just some takes of like things that I have found useful. So what I did here was I built a prediction tree. So I took the embeddings as covariates, stuck them here into a regression tree. There's different ways to do this. And I forced it at the top of the tree to split on the job category. And so at the top is the dummy variables that the economists put in their regression. But then the tree is going to split, according to predictive accuracy, into smaller subdivisions. Okay, and then I'm going to show you the most popular histories of those subdivisions. And this is a way to interpret the subdivision. So the subdivision is defined by high-dimensional uninterpretable embeddings, but I can tell you the top jobs for the subdivision, and you can put your own human name on it, okay? So manager, and this is the most predictive divisions we found in our data set. So among manager, here are the 5 most predictive subcategories. We have over here cashier and homemaker, which there are some managers, a group of managers who have cashier and homemaker in their history. This group is 93% female, and it has low wages. This group over here has software developer and electrical engineer in its history. It's 11% female, and it has high wages. And so this is an illustration of the omitted variables from the standard economist regression. If you just stuck in a manager dummy, the omitted variable would be whether you were a software manager or, maybe a maid service manager, okay? And of course, well, you could say, well, economists should just put more variables in the regression, but then you run out of data. So these methods are how do you put more variables in your regression most efficiently? Okay, so let's see, and we're about to stop, right? Let me see if I can say one more thing. In timing for this, I forgot about the Berkeley 10-minute rule. So I'm just going to show you a picture. All right. So this is the last picture, and you think she's in that case if she's going to talk about this in 1 minute, but I'm going to try. I want to just, this is like inspiration rather than full understanding is the goal here. The thing that we have been studying recently, which I think is very useful also for generative language models, is to try to understand, to do decompositions, not just of a static response, but how things change over time. So in our case, what we did is we divided up the data into 4-year buckets, and then we're looking, the first thing is we have buckets that show the raw wage gap broken into the explained and unexplained gap. So right here it's saying for people age 45 to 48, there's a very large, like 28% gap between men and women, but 22% is explained by history, and 6% is not explained by history. Okay? So we do that, and you see this gap is like growing dramatically over the age cycle. The contribution we have, the new thing we're doing, is that we are going to try to decompose the change from one to the next into 2 forces. One is the transition distribution, and one is the difference in initial conditions. And so what this shows, and I'll just pick this one for this last set of transitions, the women aged 41 to 44 are on average in more upwardly mobile jobs than men. And actually throughout the whole time, the women are in more upwardly mobile jobs than men. If you think about upward mobility defined by male upward mobility, okay? But from every transition, the women make worse transitions. And so the women, this green bar is saying that the gap is growing because women's transition distributions are different than men's transition distributions. While this part is actually shrinking the gap and working the other direction, which is the part that they were actually in upwardly mobile jobs. Okay? So this is basically, hopefully, useful to say, like, what's really happening every single time is that the women started out with a lot of potential, but don't implement on the transitions. Okay? And you can dig into that for policy. In our paper, we show that you can do heterogeneous treatment effects for this as well. Maybe just the last extra -1 minute, I will say that this green bar that we're estimating, this is the transition distribution difference. That could be, I can reinterpret this whole thing in a reinforcement learning context. So, of course, we don't have an agent telling people how to transition, but if the histories, instead of being chosen by people, were chosen by, an AI overlord, and that AI overlord was making people transition. And you could think of 2 policies the AI overlord might use. One, policy A and policy B, corresponding to, say, like the male and female transitions. And these estimates would be estimates of the off-policy evaluation of 2 different policies. If you hold the reward function fixed, here the male wage function would be like a fixed reward function, and we're evaluating the effect of different policy interventions that change the transition distribution of states. So just like a robot climbing a wall, I can have 2 different policies that change the distribution of going from one state to the next. These methods are useful, and they're better than what they've been doing in that literature for that problem. And so there's a deep connection here between reinforcement learning and this work. All right, and I will stop there. Thank you so much.
Okay, thank you, Susan. We have time for a few questions. I have a gazillion, but I will want the audience. I have time with her for dinner, so I will want questions from the audience.
There's one back there.
Just a really simple question. Thank you so much. I really enjoyed this. Just really basic. It's probably obvious to everyone else, but the subcategories, like the clusters or the sets of the clusters or the sets of previous roles or jobs, those were not temporally ordered, right? It wasn't like homemaker then cashier. It was just like present anywhere in the.
Yeah, you could do it many ways, but that's what we presented there. They were just ever present, most popular ever present.
Thank you.
But I said, by the way, I just, like, I spent a long time, I tried like 100 things to get to that graph. But like, I'm just one person. So getting this type of descriptive analysis better, I think, is really important for advancing the field. And so I have a lot of former students and friends who are working in evaluation at the big AI labs, and they're struggling with exactly these kinds of problems. So this is like a real world need for our statistical insight, even if it's not as sexy as some other ones.
So your second to last slide on the cashiers and the managers had me actually so surprised and worried in that what I thought you would want to be doing is saying, okay, you have a male software manager and a female software manager, do they make the same wage? And if not, why not? But what it seemed like the histories were adjusting for was potentially the fact that manager means very different things, and you don't have enough granularity on the manager title to be able to even say that's comparing apples and apples. So can you just sort of speak to that?
Yeah, so you can interpret that slide as an indictment of the entire econ literature that preceded it. So your comment is like evidence that they were doing it wrong, because they were putting in manager without saying what kind of manager it was. And so it's kind of like, wow, if you don't do this, you're going to be making this big mistake. You thought you were comparing apples to apples, but like, whoa, you really were not. And of course, some people did put in more granular stuff, like depending on the application, or if they were focused on a specific problem, they would do more. But it's just, yes, the answer is yes. Like you got the correct message, like that you should not do this exercise without those embeddings, because a manager is not a manager.
But it seems like the history is trying to make up for a limitation in the data.
It's trying to make up for a limitation in the data, and I'm not even sure that even with the embeddings, maybe you can partly do that, but it's not clear to me that you can even fully do that.
Absolutely. So I think that's another takeaway. I think that decomposition literature is very honest, that like, this is what I can explain with what I have. And there's always going to be stuff that I didn't get. So the literature does understand that it's missing stuff. This is just a quantification and a bit of a shocker to say, wow, you knew you were missing stuff, but like, it's not just rounding error what you were missing. And hey guys, maybe you should try out these techniques because it might help you do a better job at what you wanted to do. And the alternative to it is having your research assistant run another 500 regressions, putting in variations of managers, but like maybe there's a better way.
I was wondering about, in some sense, the open science aspect of this, in the sense that, let's say that what economists did over the years, they said, if you're just going to have a dozen variables, experience matters and all of this. And part of what you've done here, you've given us a much richer understanding of what matters to predict. And it'd be nice if then a dozen other researchers can use this and not reinvent the wheel. So is there, when he was just telling people what 12 variables to use, that was easy. Like, what are ways that we can sort of share this sort of predictive model so that others can take advantage of that?
I'm so glad you asked. There's a few challenges, like with the scraped data is like somewhat proprietary, but like hypothetically, instead of like sharing a regression table, you could share a foundation model, a trained foundation model fine-tuned on some data set. And actually, this could be amazing for open science if we could solve the privacy problem. But we don't know how to do that yet, despite the fact that all the great work people were doing at Microsoft in the 2000s on this problem. And it's advanced a huge way, but it's not quite there yet. But so right now, I don't feel good doing it like on a proprietary health data set. But in principle, one reason we're doing this, I have another paper where we actually are going to put up a fine-tuned version of Llama that is like trained on US data that's publicly available. And that way, you can save your 24 GPU hours. Maybe you don't have GPUs. Maybe it's also just useful for multiple people to use the same one. Maybe it can be plug and play. So that's another reason, I think, from a scientific process perspective, I actually think it is useful for us to decompose the problem into like the embedding part and then like the downstream task. And fine-tuning lets you make that link. And that's actually kind of sad for me, because my very popular software like made all one big machine that was a causal machine. And now I'm saying, actually, no, you don't even need a software package like my GRF package. Like, actually just use the standard tools and just change the equations you use to estimate them and change the data sets you use. So I guess but the bottom line is, I think this has broad implications for open science, and we all will together figure out the architecture of like what we post. Like, we post replication data, maybe we post a trained foundation model, and maybe we have repositories of fine-tuned foundation models. Like, and the embedding is like an API though. Like, if I know what functional form you used for your model and I know your weights, I can just plug that into off-the-shelf packages and use it. So I think this is like a really deep idea that like embeddings and foundation models are the API that would have taken us decades to build if we wanted to like make translations between all these different data sets. This data set means this means that. Like, they don't have the same variables, blah, blah, blah. In principle, like, it's a common language for combining and moving across data sets in a way that's incredibly operational, very low cost. So it's like very democratizing.
Okay, well, I think with that, let's thank Susan again.